In this video, we are going to find these frequently used Digamma values. Okay, if you don't know why we need these values or what is Digamma, just a slight intro is a Digamma of 1 plus x, this is defined as negative of Masonic constant plus sum from n equals to 1 to infinity of 1 by n minus 1 by n plus x. If you look at the sum carefully, you might recognize that this is also the xth harmonic number, right? Yeah, so if you ever want to find, let's say, the sum from n to any number of 1 by n minus 1 by n plus 4, let's say, to find that sum, diagram can be helpful because we know that that will just be digamma of 1 plus digamma of 5 plus gamma, right? So that's how it can be helpful. And sometimes if you have, let's say, 2n plus 1 and 2n, we can take 2 out and then n plus half will be there. In that case, diagram of 3 by 2 will be the answer plus Euler-Masonic constant. So yeah, these values can be helpful while finding different sums. Now let's see how we can find these values. Okay, now to find these values, we do have a direct approach as well given by the Gauss-Digamma theorem, but in this video we will not use that since that's a bit complicated. We'll use the Digamma summation formula, but just in case if you are curious, let me also write Gauss-Digamma theorem, which will help us to find the Digamma values directly. This says that the Digamma function of p by q will be equals to minus of Euler-Masonic constants minus ln of 2q minus of pi by 2 cot p pi by q. You can find this in the Wikipedia also. And then plus 2 times sum from k equals to 1 to ceiling function of q by 2 minus 1 and then cos. See, this is too complicated, so that's why I wasn't trying to use this formula. 2 pi pk by q ln. I wondered like how could he derive such formulas? Sine pi k by q, right? Okay, so this is the formula. You can use this formula and p as 1, q as these numbers, or p as 2, q as 3 as and those numbers to find value directly. But in this video we will use a different approach. What we will do is we will use this formula, Digamma summation formula, to find all these values. And I'm doing this basically because now if in any of my other videos, if I have to use these values, I will just reference this video and then I will directly go to use the value. I will not just derive in every other videos as I have been doing till now. Okay, now this says that sum from k equals to 1 to n minus 1 of digamma k by n. If you have to find digamma k by n, in their sum from 1 to n minus 1 will be equals to minus n minus 1 of Euler-Masonic constant minus ln of n. This is the Digamma summation formula. And let's see how we can use the summation formula to find all these values that must frequently appear during the infinite sums or calculations. Let's do it then. First of all, for Digamma 1, we don't need that formula. We can find this Digamma 1 basically from the original definition itself. Just put x as 0. If you put x as 0, you get Digamma 1 as Euler-Masonic constant plus sum of 1 by n minus 1 by n, which is 0. So just Digamma of 1 is negative Euler-Masonic constant. Now for others, to find Digamma of 1 by 2, what we can do is in that formula, in that sum formula, if you substitute n as 2 and k as 1, we cannot substitute k, I'm sorry. If you substitute n as 2, sum will go from 1 to 1 of digamma k by 2, and yeah, here will be 2, here will be 2. So we get, so if we use the formula, sum digamma of k by n, let me write the formula, k equals to 1 to n minus 1. This will be minus n minus 1 or the Masonic constant minus n ln n. If we put n as 2, what we get is sum from k equals to 1 to 1 of digamma k by 2 is equals to minus of 2 minus 1 is 1, or Masonic constant minus 2 ln 2. Now since k can just be 1, so this is digamma of 1 by 2 is equals to minus over Masonic constant minus 2 ln 2. And yeah, we got digamma of 1 by 2. Yeah. Now let's see how we can find digamma 1 by 3, digamma 2 by 3. So for that we need to substitute n as 3. So let's say we'll use the same formula. If we substitute n as 3 in this formula, what we will get is sum from k equals to 1 to 3 minus 1 is 2. Digamma of k by 3, that will be minus of 3 minus 1 is 2, or Masonic constant, minus 3 ln 3. Right? After that, now this sum will be digamma of 1 by 3 plus when k is 2, digamma of 2 by 3 is equals to minus 2 times solar Masonic constant minus 3 ln 3. But now since we don't know both of them, how do we find them? To find them, we can use the fact that we know we have a reflection formula which will relate these two, their difference. Reflection formula says that digamma of 1 minus x minus digamma of x will be equals to pi cot n pi. Using the reflection formula, if we put x as 2 by 3, we get digamma of 1 by 3 minus digamma of 2 by 3 is equals to pi cot 2 pi by 3, right? And we know that pi cot 2 pi by 3 is, this will be minus pi by root 3, because cot 2 pi by 3 is minus 1 by root 3, right? Because that is also because cot of pi by 3 is 1 by 3, so that's why in the second quadrant it becomes negative. So now let's add these two. 2 times digamma 1 by 3 will be minus 2 times solar Masonic constant minus 3 ln 3 minus pi by root 3. That's why digamma of 1 by 3 will be minus solar Masonic constant minus 3 by 2 ln 3 minus pi by 2 root 3, minus of polar Masonic constant minus 3 by 2 ln 3 minus pi by 2 root 3, right? Yes, right. Okay, and now if we subtract these two, we get the value of digamma 2 by 3, and digamma 2 by 3 will be, we have to subtract as well as divide by 2, right? So if we just subtract and divide by 2, we get minus gamma minus 3 by 2 ln 3 and then plus pi by 2 root 3, right? Yeah. So we have got these values. We have already got quite a lot of values. We have got this one, this one, this one, this one. Now digamma of 1 by 4. We'll use the same formula. Right? So if we put n as 4, what will we get is sum from k equals to 1 to 3 of digamma of k by 4 is equals to minus 3. For minus 1 is 3, Euler Masonic constant minus 4 ln 4, right? And this is digamma of 1 by 4 plus digamma of 2 by 4 plus digamma of 3 by 4 is equals to minus 3 times solar mass Stoney constant minus 4 ln of 4. We know digamma of 1 by 2, right? So we can put the values and take it to other side. We get digamma of 1 by 4 plus digamma of 3 by 4 to be minus 3 solar mass Stoney constant minus 4 ln 4. Again, digamma of 1 by 2 is just minus Euler-Masonic constant minus 2 ln2. So if it goes to other side, it becomes plus Euler-Masonic constant plus 2 ln2, right? Yeah. Now let us simplify this. Minus 3 Euler-Masonic constant, this is minus 8 ln2 plus Euler-Masonic constant plus 2 ln2. That's why it is minus 2 times Euler-Masonic constant minus 6 times ln2, right? This is digamma of 1 by 4 plus digamma of 3 by 4. Now if we use the other formula, reflection formula, what is it? In the reflection formula, if we use x as 3 by 4, this will be 1 by 4, this will be 3 by 4, and this will be pi cot and 3 by 4 pi, right? So let's use that. We substitute 3 by 4 in the reflection formula. We get digamma of 1 minus 3 by 4 is 1 by 4 minus digamma of 3 by 4 as pi cot 3 by 4 pi, right? And this is 3 by 4 pi is just minus 1, so this is minus pi, right? Now from here we can find the values of digamma 1 by 4 and digamma 3 by 4. Digamma 1 by 4 will be the half of the sum of both of these, right? If we sum both of them, we will have 2 times digamma 1 by 4, and again we have divided by 2. That is minus Euler-Masonic constant minus 3 ln2 minus pi by 2, right? Minus Euler-Masonic constant minus 3 ln2 minus pi by 2. And now for digamma 3 by 4, we have to subtract second from first and then divide by 2, right? If we do that, this will be minus Euler-Masonic constant minus 3 by ln2 and then subtraction, mix it plus and then plus pi by 2, right? Minus Euler-Masonic constant minus pi 3 ln2 plus this is plus pi by 2, I guess. So yeah, okay. Now we have found out digamma 1 by 4 and digamma 3 by 4 as well, right? Now we have two more to go. Digamma 1 by 6 and digamma 5 by 6. So for that, let us first place these values in a single place so that it will be easier for us, because I know we are going to need these values now. Let me quote it and let me paste it over here. Oh, I cannot move this? Oh, my bad. Then okay, doesn't matter anyway. Let me just erase that, then delete it. Okay, so I will just like look and take the value whenever I need. Yeah. So now let us try to find the last one. 1 by 6 and 5 by 6. For that, okay, wait, I need to zoom it a little bit. Yeah, let me zoom. Okay. Now for the last one, we know that sum from n equals to 1 to sum from k. Sum of k equals to 1 to n. We'll take n as 6 now. 5 of digamma k by 6 will be minus 5 Euler-Masonic constant minus 6 ln 6, right? Over here we will have digamma 1 by 6, digamma 2 by 6, digamma 3 by 6, digamma 4 by 6, digamma 5 by 6 is equals to minus of Euler-Masonic constant minus 6 ln 6, right? Now we have all of these values, we just don't have this other two. So we will just write other two as it is, and we see that again those can be found using the reflection formula. Let's find this. We know that this is diagonal 1 by 3, and the value of diagonal 1 by 3 is minus Euler-Masonic constant minus pi by 2 root 3. Sorry, I have to zoom out a bit, I guess. Okay. This is minus of Euler-Masonic constant minus 3 by 2 ln 3 minus pi by 2 root 3, right? And diagamma of 4 by 6, 2 by 3 is negative Euler-Masonic constant, negative of 3 by 2 ln 3, and then plus pi by 2 root 3, right? And diagamma of 3 by 6 is diagamma 1 by 2, which is negative of Euler-Masonic constant minus 2 ln 2, right? And okay, yeah, now this one is already here, and this will be equals to, now this will be equal to minus 5 Euler-Masonic constant minus 6 ln 6, right? So diagamma 1 by 6 plus diagamma 5 by 6 will be equals to minus 5 Euler-Masonic constant, and then there will be 3 minus Euler-Masonic constant, which when go to other side becomes plus 3 Euler-Masonic constant. Now minus 6 ln 6, and this minus 3 by 2 becomes minus 3, so there will be plus 3 ln 3 plus 2 ln 2, and then this to cancel out. Is it just that? Yeah, looks like minus 5 gamma plus minus 5 Euler-Masonic constant plus 3 Euler-Masonic constant, plus 3 ln 3 plus 2 ln 2, and these two cancel out. Okay, yeah, looks fine. Now this will be equal to minus 2 times Euler-Masonic constant, and for this one this will be minus ln of 6 to the power 6 by 3 to the power 3 dot 2 to the power 2, right? Yeah, so that will be minus 2 times Euler-Masonic constant minus ln of, it's 3 to the power 6 to the power 6, right? So this is now 3 to the power 3 2 to the power 4. So that is minus 2 Euler-Masonic constant minus 3 ln 3 minus 4 ln 2. Okay. Oh, I could have just broken it over here itself. Why did I do so miss? Fine. Okay, now this is diagamma of 1 by 6 plus diagamma of 5 by 6, right? Now again from reflection formula, if I substitute x as 5 by 6, I get diagamma 1 by 6 minus diagamma 5 by 6 as pi cot 5 pi by 6, right? And we know that 5 pi by 6 is just minus root 3. So this is minus root 3 times pi. If we add these two equations, we get, and divide by 2, we get diagamma 1 by 6 as negative Euler-Masonic constant negative 3 by 2 ln 3 negative 2 ln 2 minus root 3 by 2 pi. We get this, right? Negative minus 3 ln 3 minus 2 ln 2, yeah. And if we subtract the second from the first one and then divide by 2, we get diagamma of 5 by 6 as negative Euler-Masonic constant negative of 3 by 2 ln 3 negative of 2 ln 2 plus root 3 by 2 pi. Yeah. Oh, yeah, this is the answer. So we have found diagamma 1 by 6 and diagamma 5 by 6 as well. So in this way, we have finally found all the frequently used diagamma values, right? And this was just from the same single formula, diagamma summation formula. So we see that this formula is really helpful, not just to sum the diagammas, but also to find individual digammas as well. And we saw how we can do that. So yeah, so with these values we can do a lot of sums. These appear almost everywhere if you are dealing with infinite sums with denominators. Yeah, and yeah, I think this will be helpful in your upcoming summation journey. Hope you enjoy it. Thanks for watching, and look forward to seeing you in the upcoming videos too.